series and convergence. In this section, we talk about first the definition of a series and how is it possible for a series to converge or diverge for that matter. And then we look at three very important series. One, the telescoping series. Secondly, the geometric series. And then we talk about how to apply the nth term test for divergence for an infinite series. First, we give the definition of an infinite series. Say, for example, from the previous section, we talked about a sequence, a sub n. And I want you to understand that the convergence and divergence of a sequence has nothing to do with the convergence or divergence of a series, because the series is said to be the summation of the terms for the sequence. And so obviously the end result of the series is a little bit different than the end result of individual terms as is in the discussion for a sequence. So when you add up all of those terms, then the outcome is totally different. So here, the series is said to be the summation of a sequence. Look at the difference here. The capital S denotes the sum. So the sum 1 is said to be just the sum of the term for one sequence value. S sub 2 is said to be a sub 1 plus a sub 2. The sum, capital S sub 3, is said to be a sub 1 plus a sub 2 plus a sub 3, and so on. Now the definition for a convergent or divergent series. For the infinite series, the summation, as n goes from 1 to infinity, of a sub n, the nth partial sum is set to be s sub n, where s sub n is equal to the addition of all the sequence values a sub 1 to a sub n. If the sequence of partial sums converges to s, then the series itself is said to converge, and we call the limit s. S is the limit of the series. Another phrase for that is just the sum of the series. If the nth term of partial sums is divergent, then we say that that the series diverges. So if the nth partial sum of the sequences diverges, then the series diverges. There are three items here that we will deal with: telescoping, geometric, and the nth term. First, let's deal with the telescoping series. A telescoping series has the form whereby, if you look at this example here, b sub 1 minus b sub 2 plus b sub 2 minus b sub 3 plus b sub 3 minus b sub 4, and so on, continues on in infamy. Now, what is important here that you notice is that as you look through the telescoping eye from the beginning to the end, the terms in the middle cancel out. And you'll be left with the first term and what we call the nth or the nth plus 1 term that you want to pay special attention to. So here the b sub 2 and b sub 3 cancels out. So the nth term remains and the first term. So we say that the sum s of n is equal to the first term minus what happens toward the end. Now, I'm taking the limit of what happens toward the end because the first term is a constant, and the limit of a constant is a constant. S here, s sub n, the limit of s sub n is said to be s. So that's equal now to this limit is the first term minus the limit of those remaining terms as you continue by letting n go to infinity. Well, how does that work? Well, let's see. Find the sum of the convergent series. Now, I will tell you this, you will know when to use telescoping is because here the series, the sequence term, will beg you to break it down by using partial fractions. So for the telescoping series, use partial fractions to decompose the rational expression. Let's see. So here, in using partial fractions, this is 4 over n times n plus 2. Trying to get these pens makes me sick. So this is a over n plus b over n plus 2. Just good old partial fractions. So here, this implies that 4 is equal to a times n plus 2 plus b times n. If you let n equal to 0, if n is equal to 0, then we have 4 is equal to 2a. A is equal to 2. Also, if you let n equal to -2, then we get 4 is equal to -2 times b. That implies that b is equal to -2. So the series, look, the a is 2, the b is -2, so you can write the series now as n goes from 1 to infinity of a, which is 2 over n minus, that's -2 is the b, over n plus 2. Now we list out these terms. We count as n goes from 1, so here this gives us 2 minus 2 over 3, plus when n is equal to 2, we get 2 over 2 minus 2 over 4. So this n is equal to 1, n is equal to 2. Now when n is equal to 3, we have 2/3 minus 2 over 5 plus, you kind of get the idea. This is n equal to 1, n equal to 2, n equal to 3, n equal to 4. Let's put one more in there. So this is 2 over 4 minus 2 over 6 plus, and so on, plus 2 over n minus 2 over n plus 2, and it keeps on traveling. Now notice here that the 2/3 cancel out. 2 over 4 cancels out. And as you keep on traveling, you notice that all these terms cancel out too. So if that be the case, then we can write and think about this as S of n is equal to 2 plus, this is 2 over 2, which is 1, right? Then minus this last term out here. We're trying to match it up to the form. So, so minus this 2 over the n plus 2. Let's go back and I want to show you that. So this S of n is equal to b sub 1 minus b here sub n plus 1. So this is this minus 2 over n plus 2. And if you want, you can even write this guy right here as the b sub n plus 1, and that's fine. But so here, s is equal to 3 minus the limit as n goes to infinity of 2 over n plus 1. Okay. Well, what's the limit as n goes to infinity of 2 over n plus 2? Excuse me. I said something else, but I wrote the right thing. This limit here goes to 0. Right? So our sum is equal to 3. Interesting. Now, this was in the section, and this was another problem. It says determine the convergence or divergence of the series. Look at this and look at this. They look to be the same. Well, they started off different, but we broke this down by using partial fractions. We got the 2 there and the 2 there, so a little bit different, right? So here it says determine the convergence or divergence of the series. Well, no problem. We got the 1 there and the 1 there. This is telescoping. So we're going to write these terms out. They've already used partial fractions for us. Thank you. So, like Jimmy Fallon, thank you. So we plug in n is equal to 1, so we get 1 minus 1 over 3, plus when n is equal to 2, we get 1/2 minus 1/4. Thank you. Plus, plus n is 1. I lost my count. N is 2. N is 3. Get 1 over 3 minus 1 over 5. And you can keep on doing it, but I think you get the picture. Plus, and so on, plus 1 over n minus 1 over n plus 2, plus and so on. So notice here what cancels: the 1/3, right? The 1/4 would have canceled if we had counted again. The 1/5 cancels. That term cancels. So we look at this guy, and that term. This term right here helps us with the limit, and that means that the form of whatever happens after this takes on this pattern. Okay. So S sub n, red is not good, red is not good, red is on base 1. Okay, so this is 1 plus 1/2 minus 1 over n plus 2. So this is equal to 3 over 2 minus 1 over n plus 2. So the limit, the sum, is equal to 3 over 2 minus the limit as n goes to infinity of 1 over n plus 2. The limit here, the limit part goes to 0. So the sum is 3 over 2. If you're able to calculate and pinpoint a sum for a series, the sum is equal to this number. That's the limit. If that's the limit, it converges. So determine the convergence or divergence. Here we get a sum. Hence, convergence. Now I could have cheated, and I hate to use that word, but I could have said by the telescoping method, this series converges, right? And that would have been cool. Okay, so now I'll come back and we'll talk about geometric series, and then after that we'll talk about the nth term test. I love the nth term test. It is cool. Man, as if I've created that myself. Thank you.